we're on alternate segment theorem. Okay, the theorem is used when you have a triangle inscribed in a circle such that one of the vertices, that a tangent line to that circle passes through that vertex. So it states that if a triangle is inscribed in a circle such that a tangent line passes through one of the vertices of the triangle, then the angle made by the chord and the tangent line is congruent to the opposite interior angle of that triangle. Okay, this is just grammar. Let's see the diagram. Okay, we'll look at two different diagrams, but that same thing, that same theorem applies to this, because we are seeing triangle ABC inscribed in this circle such that this tangent line, the point of tangency, is common to the triangle and the tangent line. So that same way, that's the triangle. So the point of tangency is C, and a tangent line passes through it. So we are saying that the angle formed by the chord, say the chord, and the tangent line, which is θ1, or another chord, and the tangent line, which is θ2, is equal to opposite interior angle. So that's exterior, this outside, this interior, opposite that one. So do you get? It's just opposite. So that same way, if you enter, is opposite to that. So it's very clear. Once you have this, the angle from here, just look at straight opposite. That's it. That's so let's just prove that. Okay, let's prove that we have the same. We have a circle and an inscribed angle ABC. So want to prove that θ1 is equal to θ2. Okay, we have the center of this circle to be O. So I will add two auxiliary lines here. So let's add it. Okay, that's the lines. So let's call the diameter CF. Okay, let's call this F. So we see that by inscribed angle theorem, or Thales theorem, by Thales theorem, this angle is 90. Yes, because this is 180. That's the diameter. This is 180. And angle at the center is 2 times that of the inscribed. So here is 180, here is 90. So that's the first thing. And by Bose theorem, here is θ1. Here also with θ1. Yes. Yes, see the intercepted arc. The two inscribed angles have the same intercepted arc. So they are equal. So finally, we have the, remember this is a tangent line, and this is my radius of the circle, or diameter. So the radius is always perpendicular to the tangent line. So if here is 90, the sum here must be 90 to make it 180. So the remaining angle should be 90, but they gave us θ2. So our idea is to get angle FCB. So let me just write what I have said. So the first thing, we see that the angle CBF is 90 degrees by Thales theorem. So an angle CFB is θ1 by Bose theorem. So which implies that this angle, okay, this angle FCB, we have two answers. So if you take triangle FCB, the remaining angle here will be 90 minus θ1 by angle sum theory for triangle. So that same FCB is also 90 minus theta 2 based on radius tangent relationship. They're always perpendicular, the radius and the tangent line. But we are given this, since here is theta 2, here should be 90 minus theta 2. So this angle is that same angle is that. It implies that these two, so 90 minus theta 1 is the same as 90 minus theta 2. So we can see that theta 1 is equal to theta 2. So that's it. We've proved that theta 1 is equal to. So let's solve a equation on that. This question, we're asked to find the value of x. So since I'm seeing a tangent line and I'm seeing an inscribed triangle, so I will use my alternate segment theorem. So if here is x, here is x. And you know the sum of angles, interior angles of a triangle is 1/8. So x is 180 minus, which is 36. The answer is 36. So I'm saying that it's very simple that, let me write just that angle ABD is x degree alternate segment theorem. So which implies that x degree is 36. Angle sum theory for triangle, angle sum theorem for triangle. So our x we are looking for is 36, option A. So it's very quick one.